Momentum equals mass times velocity. You learned it in school. You wrote it on a test, you got it right, and you walked away thinking you understood momentum. You don't. And I don't say that to be rude. I say it because for a very long time, some of the best physicists in the world didn't fully understand it either. They had the formula. They used it every day. But they were missing something enormous hiding right behind it. Something so deep that when it was finally uncovered, it changed how we think about the entire universe. So let me take you through this properly, not the textbook way, the real way. All right, let's start where everyone starts. You've got a ball. Let's say it weighs 1 kilogram. You throw it, and it's moving at 10 meters per second. What's the momentum? 10 kilogram meters per second. Mass times velocity. Done. Now I throw a heavier ball. 5 kilograms. Same speed, 10 meters per second. Momentum, 50 kilogram meters per second. More mass, more momentum. Makes sense. Now I throw the light ball faster. 1 kilogram at 50 meters per second. 50 kilogram meters per second. Same momentum as the heavy one going slow. And that feels right, doesn't it? A small thing moving fast can pack the same punch as a big thing moving slow. So far, so good. This is what everybody learns. Mass times velocity. A bigger number means something's harder to stop. A truck at 60 miles per hour has more momentum than a bicycle at 60 miles per hour. A bullet has a lot of momentum for its size because it's going very fast. All perfectly sensible. And here's where people get comfortable. They say, okay, momentum, I got it. It's how much oomph something has, a measure of how much motion something is carrying around. Mass times velocity. Next topic. But hold on, let me push a little harder. Why do we care about this particular combination? Why mass times velocity? Why not mass times velocity squared? Why not mass times the cube root of velocity? Why not mass squared times velocity? You could invent any formula you want. Multiply mass by some function of speed. You'd get a number. But physics doesn't care about random numbers. Physics cares about quantities that mean something. Quantities that nature actually respects. So what is it about this particular combination that's special? Here's the answer most people give, and it's not wrong, but it's shallow. They say momentum is conserved. If two things collide, the total momentum before the collision equals the total momentum after. And that's true. That is a genuine fact about the world. If a big ball hits a small ball on a pool table, you can track the momentum of each ball before and after, add them up, and the totals match, every time, without exception. Let me make that concrete. Take two pool balls. One is sitting still. The other rolls toward it at 6 meters per second. They collide head-on. After the collision, the moving ball almost stops, and the stationary ball shoots forward at nearly 6 meters per second. Momentum before, the mass of one ball times 6 plus the mass of the other ball times 0. Momentum after, the first ball times nearly 0 plus the second ball times nearly 6. Same total. The momentum just passed from one ball to the other, like handing off a package. You can try this with anything. Shopping carts in a parking lot, hockey pucks on ice, toy cars on a track. Set up the collision however you want. Measure the masses, measure the speeds, calculate mass times velocity for each object before and after. The totals always match. It's like a magic trick that never fails, and it works whether the objects bounce off each other or stick together, head-on or glancing, big hitting small or small hitting big. The total momentum before always equals the total momentum after. And that's neat, it's useful. You can solve all kinds of problems with it. Collisions, explosions, rocket propulsion. It's one of the great tools of mechanics. But here's the question that almost nobody asks. Why is momentum conserved? What is it about the universe that makes this particular quantity and not some other quantity stay the same? Most people stop here. They accept conservation of momentum as a given, a rule, a fact about collisions. End of story. That is exactly where the misunderstanding begins. Let me show you the first crack in the simple picture, and it's a big one. Imagine you're standing in a dark room. You've got a flashlight. You turn it on and shine it at the wall. Light comes out, hits the wall. Seems simple enough. But if you had an incredibly sensitive instrument, you would find that when you turned on that flashlight, you got pushed backward. Very slightly, almost immeasurably, but pushed. The light shoved you. Now think about what that means. Light has no mass. Photons, the particles of light, have zero mass, not tiny mass, not almost zero, exactly zero. So if momentum is mass times velocity, and the mass of a photon is zero, then the momentum of light should be zero times the speed of light, which is zero. No momentum, nothing, and yet the flashlight pushed you. The light carried momentum, real, measurable, honest-to-God momentum. This isn't some abstract theoretical curiosity. There are serious proposals to build solar sails, enormous reflective sheets deployed in space, pushed along by nothing but sunlight. The pressure of light on a surface is extraordinarily faint. On a square meter, the force from sunlight is roughly equivalent to the weight of a grain of salt. You would never feel it. But in the vacuum of space, with no friction, no air resistance, no drag of any kind, that tiny push adds up, hour after hour, day after day, month after month. You can accelerate a spacecraft to remarkable speeds using nothing but the momentum of photons. Particles with absolutely no mass at all. In 1873, Maxwell predicted from his equations of electromagnetism that light should exert pressure. It took nearly 30 years for experimentalists to measure it. But Maxwell was right. Light pushes, and it pushes because it carries momentum. So either momentum is not really mass times velocity, or something very strange is going on with light. And this is not some exotic edge case. Light is everywhere. It is the most common thing in the universe. If your definition of momentum doesn't work for light, your definition is in trouble. Let me show you another crack. This one's more subtle, but just as important. Go back to our simple collision. Two balls on a table. They slam into each other. Momentum is conserved. Beautiful. But here's what people forget. Energy can be lost in a collision. If two lumps of clay slam together and stick, a tremendous amount of kinetic energy disappears. It turns into heat, into sound, into the deformation of the clay. You can measure the kinetic energy before and after is way less than before. The energy of motion went down. But momentum stays exactly the same. Not approximately, not roughly, exactly. How is that possible? Think about it. If momentum were just another way of measuring how much motion something has, like energy is, then losing energy should lose momentum too. They should be tied together. But they're not. Energy and momentum are independent, conserved quantities. They follow different rules. They're conserved for different reasons. And knowing one doesn't tell you the other. This should bother you. If you think of momentum as the amount of motion, then how can you lose half the motion energy but keep all the momentum? What kind of amount of motion is that? Let me make this sharper with a specific example. Take a 5-kilogram ball moving to the right at 4 meters per second. It slams into a 5-kilogram ball, sitting still. In a perfectly elastic collision, the first ball stops dead, and the second ball takes off at 4 meters per second to the right. Momentum before 20 kilogram meters per second. Momentum after 20 kilogram meters per second. Energy before 40 joules. Energy after 40 joules. Everything is conserved. Clean and tidy. But now change the collision. Make the balls sticky. They collide and stick together. One 10-kilogram lump, moving to the right. By conservation of momentum, the combined lump must have 20 kilogram meters per second of momentum. 10 kilograms times what velocity? 2 meters per second. The lump is going half as fast as the original ball. So what's the kinetic energy after? 1/2 times 10 times 2 squared. That's 20 joules. We started with 40. Half the kinetic energy just vanished. Poof, gone into heat and sound and deformation. But the momentum is exactly the same. 20 before, 20 after. So energy and momentum can behave completely differently in the same event. One gets halved while the other is perfectly preserved. That tells you they're measuring fundamentally different things. Momentum is not energy's cousin. It's not a slightly different flavor of how much motion. It's tracking something else entirely, something independent, something with its own reason for existing. And the reason it's not adding up with the simple picture is that our picture of momentum is too simple. It's too narrow. It's a cartoon version of something much more interesting. So, let me take you somewhere unexpected. I need to take you into empty space, not outer space, not stars and galaxies. I mean the space around you right now, the emptiness between objects, the stage on which everything happens, because the secret of momentum is not about objects at all. It's about space itself. Pick a spot. Any spot, call it here. Now pick another spot 5 meters to the left. Call it there. Now let me ask you a strange question. Is here any different from there? I don't mean is the furniture different. I don't mean is the temperature different. I mean, are the fundamental laws of physics different at here compared to there? If you set up an experiment here, measure everything carefully, record the results, then pick up your entire laboratory, every atom of it, move it 5 meters to the left, set it down and run the exact same experiment, do you get the same result? The answer is yes, you do. Every experiment ever conducted confirms this. The laws of physics don't depend on where you are. They are the same here as there, the same in New York as in Tokyo, the same in this room as on the surface of Mars, the same in this galaxy as in a galaxy 10 billion light years away. Now this sounds obvious, almost too obvious to be interesting. Of course the laws are the same everywhere. Why wouldn't they be? But stop. It is not obvious at all. The universe could have been set up differently. Gravity could have been stronger in one corner of the room. Electricity could have worked by different rules on the north side of the lab compared to the south. The speed of light could have been different in different regions of space. It could have been a patchwork quilt of different physics in every neighborhood. It isn't. Space is uniform, homogeneous, the same everywhere. And we've checked this. Not casually. Obsessively. Astronomers look at galaxies billions of light years away, and the light coming from those galaxies is produced by the same atomic processes that happen in labs on Earth. The spectral lines of hydrogen in a galaxy 10 billion light years away match the spectral lines of hydrogen in a tube in a university basement. Same physics, same rules, across unimaginable distances, across billions of years of cosmic time. Physicists call this property translational symmetry. If you translate, meaning shift, your entire experiment from one location to another, nothing changes. The outcome is identical, and this has been verified to extraordinary precision. Nobody has ever found a crack. Nobody has ever discovered a place where the rules are different. This uniformity of space is one of the deepest facts about the universe we live in. It is not a consequence of some other law. It is not derived from anything more basic. It just is, and it has consequences that are staggering. In 1915, a brilliant mathematician named Emmy Noether proved something extraordinary. She proved a theorem. Not a conjecture, not a guess, a mathematical theorem. Airtight and irrefutable. Noether was working at the University of Göttingen, and she wasn't even allowed to hold a proper faculty position because she was a woman. She lectured under other people's names, she was paid almost nothing, and yet she produced what many physicists consider the single most important theorem connecting mathematics to physics. It says every continuous symmetry of the laws of physics corresponds to a conserved quantity. For every symmetry there is something that cannot be created or destroyed. Let me be precise. A continuous symmetry means a transformation you can do by any amount. You can shift your lab 1 meter, or 2 meters, or half a meter, or 1/10 of a millimeter. Any amount. That's a continuous symmetry, as opposed to a discrete symmetry like flipping left and right. Noether's theorem says find a continuous symmetry, and I will hand you a conservation law. Guaranteed. No exceptions. And it works backward too. Find a conservation law, and I will find you a symmetry. Let me give you an analogy that might help this land. Imagine a perfectly flat, featureless ice rink that extends infinitely in every direction. You're standing on it. No friction. You push a puck. It slides away forever in a straight line at constant speed. Now here's the key. Because the ice is the same everywhere, it doesn't matter where you push the puck. Push it from the center. Push it from the far corner. Push it from any spot at all. Same push, same result. The puck doesn't care where it started. That's spatial symmetry. Now imagine the ice has a hill in the middle, a bump. Suddenly, it matters where you push the puck. Push it on the flat part, and it slides away cleanly. Push it near the bump, and it curves, or slows, or speeds up. The result depends on location. Spatial symmetry is broken. And guess what? On that bumpy rink, momentum is not conserved. The bump can absorb momentum or inject it. The puck can speed up going downhill and slow down going uphill. Even with no outside push, the total momentum of the puck changes because space is not uniform. This is not just an analogy. This is exactly what happens with gravity. A ball falling toward the Earth is gaining momentum. Where does that momentum come from? From the gravitational field, from the fact that space near the Earth is not the same as space far from the Earth. The symmetry is broken, and so momentum of the ball alone is not conserved. You have to include the Earth and its field in the accounting. When you include everything, the symmetry is restored and the total momentum, ball plus Earth, is conserved again. So Noether's theorem doesn't just tell you that momentum is conserved, it tells you precisely when and why it would fail to be conserved, when the symmetry is broken. That's an enormously powerful diagnostic tool. And here's the punchline. The translational symmetry of space, the fact that the laws of physics are the same at every location, corresponds to the conservation of momentum. That is why momentum is conserved. Not because of some property of collisions, not because of some accounting trick with mass and velocity. Momentum is conserved because space is uniform. Take a moment with that. The reason a billiard ball transfers momentum to another billiard ball is that the laws of physics don't change as you move from one place to another. The reason a rocket works, the reason an explosion conserves momentum, the reason every collision in the history of the universe has balanced its momentum books, is that space looks the same here as it does 5 meters to the left. That is the deep reason, the real reason. Everything else is a consequence. And Noether didn't stop there. Her theorem gives us more. The fact that the laws of physics are the same today as they were yesterday, that's time symmetry. And time symmetry gives us conservation of energy. The fact that the laws of physics don't change when you rotate your lab, face it east instead of north, that's rotational symmetry. And rotational symmetry gives us conservation of angular momentum. 3 symmetries, 3 conservation laws. Space uniformity gives momentum. Time uniformity gives energy. Rotational uniformity gives angular momentum. The 3 most important conservation laws in all of physics, and they come from the 3 most basic symmetries of the universe. That's not a coincidence, that's the structure of reality. And it keeps going. In particle physics, there are more exotic symmetries, internal symmetries having to do with the way particles transform under the forces of nature. And each of those symmetries gives its own conserved quantity. Conservation of electric charge comes from a symmetry. Conservation of a quantity called baryon number comes from a symmetry. Every conservation law you've ever heard of, and several you haven't, traces back to a symmetry through Noether's theorem. It is the master key that unlocks the entire cabinet of conservation laws. And here is why the clay collision makes sense now. Remember, 2 lumps of clay slammed together, kinetic energy is lost, but momentum is conserved. Earlier that seemed contradictory. How can you lose one measure of motion but keep the other? The answer is that energy and momentum come from different symmetries. Energy comes from time symmetry. Momentum comes from space symmetry. They're independent. Losing kinetic energy in a collision doesn't violate time symmetry, because the energy didn't vanish, it turned into heat and sound and deformation. Total energy, including the thermal energy, is still conserved. And the collision doesn't violate spatial symmetry at all, so momentum is perfectly conserved in its visible mechanical form. They're separate books, kept by separate accountants for separate reasons. Once you see this, the whole landscape of physics reorganizes in your mind. And now let me go further. Let me show you what momentum looks like in quantum mechanics, because this is where the old picture really falls apart. In quantum mechanics, particles don't have definite positions. You've heard this before. An electron is not a little ball sitting at a specific spot. It's described by a wave function, a mathematical object spread out across space. This wave function tells you the probability of finding the electron in various places if you go looking for it. It's a cloud of possibility. And here's the remarkable thing. The momentum of a quantum particle is not mass times velocity. You cannot even define velocity in the usual way for a quantum particle because it doesn't have a definite position moment to moment. So how would you track how fast it's going from one spot to another? Instead, the momentum is determined by how the wave function changes across space. Specifically, it depends on the wavelength of the wave. Short wavelength, high momentum. Long wavelength, low momentum. Very tightly packed oscillations mean the particle is carrying a lot of momentum. Gentle, spread-out waves mean very little momentum. Think of it like sound. A high-pitched note has a short wavelength. The air pressure oscillates rapidly from one point to the next. A low-pitched note has a long wavelength. Gentle, slow oscillations. The momentum of a quantum particle works the same way. A high-pitched wave function corresponds to high momentum. A low-pitched one corresponds to low momentum. The analogy isn't perfect, but it gives you the flavor. This is completely different from mass times velocity. There's no velocity in the picture at all. There's just a wave and how rapidly it oscillates from point to point. And yet it's the same momentum, the same conserved quantity. It obeys the same conservation laws. It transfers the same way in interactions. The definition changed, but the deep identity, the thing that Noether's theorem guarantees, stayed exactly the same. And from this quantum picture of momentum, you get something remarkable for free. The Heisenberg uncertainty principle. Listen to how naturally it falls out. If you want to know exactly where a particle is, you need its wave function to be concentrated in a very small region, squeezed into a tiny spike. But think about what happens when you squeeze a wave into a tiny space. To be confined to a small region, the wave function has to change very rapidly. It has to oscillate like crazy to fit into that small area. And rapid oscillation means short wavelength, and short wavelength means high momentum, or more precisely, it means the particle could have high momentum or negative high momentum, because the wave has to have many different wavelengths mixed together to make that tight spike. So by pinning down the position, you've made the momentum completely uncertain. It could be anything. And it works the other way too. If you want a particle with very definite momentum, you need a nice clean wave with a single wavelength. But a single wavelength wave extends forever in both directions. It's not localized at all. It's everywhere and nowhere. So you know the momentum precisely, but you have absolutely no idea where the particle is. That is the uncertainty principle. And notice there was no hand waving. No appeals to the act of measurement disturbs the particle. No philosophical mumbo-jumbo about consciousness or observers. It's just mathematics. It's just what happens when momentum is defined by the spatial structure of waves. The uncertainty principle is a direct mathematical, unavoidable consequence of what momentum really is. And this has real consequences, not just philosophical ones. The uncertainty principle, flowing directly from the nature of quantum momentum, explains why atoms don't collapse. Think about a hydrogen atom. One proton, one electron. The proton is positive, the electron is negative, and they attract each other. So why doesn't the electron just spiral into the proton and sit on top of it? In classical physics it should, but in quantum mechanics, if the electron's position is squeezed down to a very small region near the proton, its momentum becomes wildly uncertain. An uncertain momentum means the electron has a high average kinetic energy. The closer you push it, the more violently it jiggles. At some point, the kinetic energy from the jiggling balances the attractive energy from the electric force, and you get a stable atom, a specific size, a specific energy. The size of a hydrogen atom, about 0.05 of a nanometer, is determined by this balance. And that balance exists because momentum in the quantum world is tied to spatial variation. Squeeze the space and you blow up the momentum. It's Noether's conserved quantity expressed through wave mechanics that holds matter together. That is staggering. The reason atoms have the sizes they do, the reason chemistry works, the reason solid objects are solid, traces back to what momentum really means. Now let me swing back to something more familiar. Newton's second law. Everybody knows it as F equals ma. Force equals mass times acceleration. But Newton himself didn't write it that way. Newton's original formulation was, force is the rate of change of momentum with respect to time. And this matters more than you might think. Because F equals ma and force equals the rate of change of momentum are not the same statement. They look the same when the mass doesn't change. If an object has constant mass, then the rate of change of mass times velocity is just mass times the rate of change of velocity, which is mass times acceleration. Fine, you get F equals ma, but what if the mass changes? Think about a rocket. A rocket burns fuel. It ejects hot gas out the back at tremendous speed. As it burns, its mass decreases. The rocket is getting lighter every second. So the mass is not constant. And in that case, F equals ma doesn't give you the right answer. You need the momentum version. The thrust of the rocket equals the rate at which it's expelling momentum out the back end. That depends on how fast the exhaust gas is moving and how many kilograms per second are being thrown out. You cannot get this right thinking about mass times acceleration. You need to think about momentum directly. And the rocket itself is a beautiful demonstration of momentum conservation in its purest form. Before the engine fires, the rocket and its fuel are sitting still. Total momentum 0. When the engine fires, hot gas shoots out the back. The gas carries momentum in one direction. The rocket picks up momentum in the other direction. Total momentum of the system, rocket plus exhaust gas, is still 0. Always 0. The rocket moves forward precisely because the exhaust moves backward. Nobody is pushing the rocket. There's nothing to push against in space. It pushes itself forward by throwing stuff backward. That's conservation of momentum at work, naked and undisguised. Or picture a raindrop falling through a cloud. It starts small, a tiny droplet. As it falls, it collides with smaller droplets and absorbs them. It's gaining mass as it falls. The momentum is changing, not just because gravity is accelerating it, but because the thing itself is getting heavier as it moves. F equals ma doesn't capture this. You need the rate of change of momentum. You need the full, proper statement of Newton's law. Newton knew this. He stated his law in terms of momentum deliberately. It was the central concept of his mechanics. The very word momentum appears throughout the Principia. The simplification to F equals ma came later, from textbook authors trying to make things more accessible for students. And in making things simpler, they made things less correct, less general. And in physics, less general is a kind of wrong, because the universe does not restrict itself to your convenient special cases. The universe obeys the general law, always. Let me return to light now. I left you with a puzzle earlier. Photons have no mass, yet they carry momentum. How? The answer comes from Einstein's special relativity. And it involves one of the most famous equations ever written, although not in the way most people think. Everyone knows E equals mc squared. Energy equals mass times the speed of light squared. But that equation, the famous one that appears on t-shirts and coffee mugs, is a special case. It only applies to objects sitting still. It tells you the energy locked inside a stationary lump of mass. The full equation, the one Einstein actually derived, is richer. It says E squared equals P squared times C squared plus M squared times C to the fourth. E is total energy, P is momentum, M is rest mass, C is the speed of light. Look at that equation. Energy and momentum are bound together. They appear in the same formula. They're two pieces of one mathematical object. Now see what happens for a photon. The rest mass of a photon is 0. Set m to 0. The equation simplifies beautifully. E squared equals P squared times C squared. Take the square root. E equals P times C. Rearrange. P equals E divided by C. The momentum of a photon equals its energy divided by the speed of light. And there it is. Light carries momentum not because it has mass, but because it has energy. In relativity, energy and momentum are not separate, independent things you bolt together. They are two components of a single object. Physicists call it the energy-momentum four-vector. Energy is the time component. Momentum, all three directions of it, is the space component. Just like time and space themselves are fused together into space-time, energy and momentum are fused into a single four-dimensional quantity. You cannot have a complete description of anything's state of motion without specifying both. This is elegant in the deepest sense. And it's why the simple formula momentum equals mass times velocity was always incomplete. It works for everyday objects, yes, but it misses the architecture. The real story of momentum lives in the geometry of space-time. And once you accept that energy and momentum are tied together, something else follows that most people never consider. Fields carry momentum, not just particles. Fields, think about two magnets, hold them near each other with like poles facing. They push apart. Where is the force coming from? There's nothing between them. No rod, no spring, no contact. The force is carried by the electromagnetic field that fills the space between the magnets. And that field, that invisible thing that you can't touch or see, carries momentum. Real momentum. The electromagnetic field between those magnets has momentum just as surely as a thrown baseball does. James Clerk Maxwell figured this out in the 1860s. He showed that electromagnetic fields carry both energy and momentum. Light is an electromagnetic field. A radio wave is an electromagnetic field. The microwave radiation left over from the Big Bang, filling all of space, carries momentum. So does the magnetic field of the Earth, and the electric field between the plates of a capacitor. This is why momentum equals mass times velocity is not just incomplete for photons. It's incomplete for the entire electromagnetic field. There's an ocean of momentum in the universe that has nothing to do with mass or velocity. It's sitting in fields, in the spaces between things. In the vacuum, momentum is not a property of matter alone. It's a property of anything that exists in space, anything that the translational symmetry of space can act upon. Let me give you one more example that ties everything together. Think about an explosion. A bomb goes off. Before the explosion, everything is sitting still on a table. Total momentum, 0. After the explosion, fragments fly in every direction. North, south, east, west, up, down. Every fragment carries momentum. But add up all those momenta, all the vectors, carefully accounting for direction, and the total is 0, exactly 0. Same as before. Think about how remarkable that is. An explosion is violent and chaotic, completely uncontrolled. The fragments don't know about each other. They're not communicating, they're not coordinating. The hot gases and shrapnel fly every which way. And yet, every single time, in every explosion that has ever happened in the history of the universe, the momenta balance perfectly. How does nature manage this? The answer is Noether. It's not that the fragments are cleverly arranged. It's that the laws of physics don't change from place to place. The explosion would happen the same way if you moved the bomb 3 feet to the left or to another room or to another planet. That spatial uniformity makes it mathematically impossible for the total momentum to change. It is not a coincidence. It is not luck. It is geometry. The geometry of space itself, expressing itself through flying shrapnel. And this works everywhere. In every collision, every explosion, every nuclear reaction, in the enormous accelerators where protons are smashed together at nearly the speed of light. In those collisions, hundreds of new particles burst into existence. Particles that weren't there a moment before. Particles genuinely created from pure energy. And the total momentum before the collision equals the total momentum after. Exactly. Every single time. Down to the limits of measurement. Because space has not stopped being uniform. Noether's theorem does not take a day off. Let me bring this down to something physical, something you can feel. That catching a baseball, the ball is coming at you, it has momentum. You catch it, the ball stops. Where did the momentum go? Into your glove, into your hand, your arm, your shoulder. You rocked backwards slightly. Your feet pushed against the ground, and the ground pushed back. If you're standing on the earth itself recoiled. By how much? An incomprehensibly tiny amount, something like 10 to the minus 25 meters, smaller than an atom, smaller than a proton. Nobody would ever measure it. But the earth moved. The mathematics demands it, and the mathematics is right. But here's the subtlety that matters in the real world, the part that saves lives. When you caught that ball, the force on your hand depended on how quickly you stopped it. If you held your glove stiff and rigid, snap, the ball stopped in a tiny fraction of a second. The force was enormous, and your hand stung. If instead you let your arm give way, let your elbow bend, cushioned the catch, the ball stopped over a longer time. Same total momentum transferred, exactly the same amount, but the force was much smaller. Your hand felt fine. This is the impulse-momentum relationship. Impulse equals force multiplied by time, and impulse equals the change in momentum. So you can transfer the same momentum with a huge force over a short time, or a gentle force over a long time. The momentum change is identical, the force is not. And this is why cars have crumple zones. Think about what a crumple zone actually does. In a crash, the car is going to stop. The momentum is going to be transferred to whatever it hits. There's no negotiating with Noether's theorem on this. The momentum will be conserved whether anyone likes it or not. What the crumple zone does is extend the time over which that stop happens. Instead of the car going from 60 miles per hour to 0 in a tenth of a second against a concrete wall, the metal crumples and folds and crushes, and the car comes to rest over half a second, maybe a full second. Same change in momentum, but 5 or 10 times more time means 5 or 10 times less force. And that is the difference between walking away from a crash and not walking away. Every safety device humans have ever built works this way. So, airbags inflate and then slowly deflate as you press into them. So that's extending the time. Bicycle helmets have a layer of foam that crushes on impact. That's extending the time. A gymnast bends her knees when she lands a vault. That's extending the time. Bungee cords stretch. Boxing gloves compress. The net under a trapeze artist sags. All of them, every single one. They increase the time over which momentum is transferred, and by increasing the time they decrease the peak force. Think about eggs. If you drop an egg onto a concrete floor from waist height, it shatters. The stop happens in 1,000th of a second. Enormous force. Broken shell. But drop that same egg from the same height onto a thick pillow and it survives. The pillow compresses. The egg decelerates over 1/10 of a second, maybe longer. That's 100 times more time, 100 times less force. Same egg, same height, same momentum change. The only difference is how much time you gave nature to do the job. The momentum itself is non-negotiable. Nature has locked that in, but the time is something you can manipulate. So we manipulate time to survive the momentum. I find this extraordinary. People think of car safety engineering as practical and boring, mundane. But underneath every crumple zone is Noether's theorem. Underneath every airbag is the homogeneity of space. The reason your car is designed the way it is traces a direct line back to the fundamental symmetries of the universe. You survived your last fender bender because space looks the same at every point. You just didn't know it. Let me go one layer deeper. I've been talking about linear momentum, the kind associated with straight-line motion through space. But Noether's theorem gives us another gift. Rotational symmetry, the fact that the laws of physics don't care which direction you're facing, gives us conservation of angular momentum. Think about an ice skater spinning. She starts with her arms stretched wide. She's rotating slowly. Then she pulls her arms tight against her body, and she spins dramatically faster, almost instantly. She didn't push off anything. Nobody wound her up like a toy. She just moved her arms. How did she speed up? Angular momentum depends on three things. How much mass is moving, how far that mass is from the axis of rotation, and how fast everything is spinning. When the skater pulls her arms in, the mass that was far from her center moves close to her center. The distance from the axis decreased. But angular momentum has to stay the same because rotational symmetry hasn't gone anywhere. The universe is still isotropic, so if the distance decreases, the spin rate must increase to compensate. She spins faster, not because of a motor, not because of a push, because the universe will not let angular momentum change unless something from outside acts on the system. The same principle explains why planets orbit the way they do. When a planet swings close to the sun in its elliptical orbit, it speeds up. When it recedes to the far reaches of its orbit, it slows down. Kepler noticed this pattern in the early 1600s. He described it as a geometric law. Planets sweep out equal areas in equal times. But the real explanation is conservation of angular momentum. When the planet is closer, the distance to the axis is smaller, so the speed goes up. When it's farther, the distance is larger, so the speed comes down. The angular momentum stays constant throughout the orbit. And the reason it stays constant is that gravity is a central force, pointing straight at the sun, which means it respects rotational symmetry. Noether's theorem again. Always no other. You see angular momentum conservation in the strangest places once you start looking. A spiral galaxy keeps its shape because of angular momentum. A neutron star spins hundreds of times per second because the massive star it came from had angular momentum. And when that star collapsed to a tiny fraction of its original size, like the skater pulling in her arms, the spin rate exploded. A tornado forms because a large, slowly rotating mass of air gets funneled into a narrow column, concentrating the angular momentum into a smaller radius, which drives the devastating wind speeds. These are all the same physics, the same symmetry, the same conservation law, playing out at scales from the subatomic to the galactic. So now step back. Look at the whole picture. Translational symmetry gives us conservation of linear momentum. Rotational symmetry gives us conservation of angular momentum. Time symmetry gives us conservation of energy. 3 symmetries, 3 conservation laws. And those 3 conservation laws are the skeleton of classical physics. They are the constraints that every physical process must obey. They tell you what's possible and what's forbidden before you solve a single equation of motion. That is the real power of conservation laws. They don't depend on the messy details. If a system is too complicated to analyze force by force, particle by particle, you can still use conservation of energy and momentum to constrain what can happen. And those constraints come from symmetries that hold no matter how complicated the system gets. 10 particles or 10 trillion, billiard balls or galaxies. The symmetries are always there, and the conservation laws always apply. This is why physicists are obsessed with symmetry. Not because we think symmetric things are pretty, although many of us do, because symmetry tells us what is conserved, and what is conserved tells us what is possible. It's the deepest, most reliable tool we have for understanding nature. Now, let me come back to where we started. Momentum equals mass times velocity. Is that wrong? No, it is not wrong. It's limited. It works beautifully for everyday objects moving at everyday speeds. But it is a tiny window into a vast landscape. The real story of momentum is this. The universe has a property. It looks the same no matter where you are. Move your experiment to the left, to the right, up, down, halfway across the cosmos. It doesn't matter. The laws don't change. This spatial uniformity, this translational symmetry, mathematically guarantees, through Noether's theorem, that there exists a conserved quantity associated with motion through space. We call that quantity momentum. For slow, massive objects, this conserved quantity reduces to mass times velocity. That's the special case everyone learns. For light, it's energy divided by the speed of light. For quantum particles, it's related to the spatial frequency of the wave function. In general relativity, it becomes even more subtle because space itself is curved, and you have to be exceedingly careful about what same everywhere means on a curved background. But in every case, every regime, every theory we have ever constructed, it's the same deep thing. The conserved quantity that arises because space is uniform. If you learn momentum as mass times velocity, you can pass a physics test. But you miss the connection to symmetry. You miss the reason light can push things. You miss the quantum wave picture. You miss the intimate relationship between energy and momentum in relativity. You miss the reason safety devices work. You miss the reason rockets fly and ice skaters spin faster. You miss the architecture that holds all of physics together. And here's what I find most beautiful about all of this. We did not invent momentum. We discovered it. It was there before we had a name for it. Before there were people, before there were planets. The uniformity of space, the symmetry that gives rise to momentum conservation, that is a property of the universe itself. It is woven into the fabric of reality at the deepest level anyone has ever been able to probe. We just figured out how to notice it. Emmy Noether figured out the mathematical connection. Einstein showed how momentum and energy belong together in relativity. Heisenberg and Schrödinger showed what momentum means in the quantum world. But the symmetry was always there, the conservation was always operating. Every collision that ever happened, every photon that ever nudged a surface, every explosion that ever scattered its debris, obeyed a law that flows directly from the geometry of space. And not a single one of those events needed a physicist to supervise it. So the next time someone tells you momentum is mass times velocity, you can nod politely. They're not wrong, but they're looking at the shadow on the wall. The real object, the thing casting that shadow, is much larger, much deeper, and much more beautiful than any formula chalked onto a blackboard. If there is one thought I would want you to carry away from all of this, it's this. The most important things in physics are not formulas. They are symmetries. The formulas come from the symmetries, not the other way around. And once you see that, once you truly see it, you never look at the world the same way again. You start noticing it everywhere. A spinning top stays upright because of angular momentum. A firefighter's hose kicks back because of momentum. A swimmer pushes water backward and moves forward because of momentum. A squid jets through the ocean by expelling water behind it. The recoil of a gun, the motion of a rowing boat, the way a cat twists in midair to land on its feet, which, by the way, is an angular momentum problem that confused physicists for decades. All of it is the same principle. All of it is Noether's theorem, applied to translational and rotational symmetry, playing itself out in 1,000 different guises. And the formula P equals mv, that is just one costume the principle wears. The simplest costume, the one suitable for slow, heavy, everyday objects. But the principle underneath, the symmetry underneath, wears many costumes. It dresses up as wave functions in quantum mechanics, as four vectors in relativity, as field momentum in electrodynamics, as angular momentum in rotating systems. Different clothes, same body, and the body is symmetry. So let me ask you this. Before today, if someone put you on the spot and asked what momentum is, what would you have said? And right now, after everything we've walked through, how would you answer instead? I'd like to know what shifted in your thinking.